Hi class, welcome back to Multivariate Calculus. In this lecture, we are going to be returning to evaluating triple integrals, but this time we are going to be converting from Cartesian coordinates to both cylindrical and spherical coordinate systems. But before we get into that, let's start with a warm-up. And for this warm-up, I'd like you to find the volume of the solid that is under the hemisphere. Z is equal to the square root of 1 minus x squared minus y squared, and above the region bounded by the graph of the circle x squared plus y squared minus y equals 0. Now, you can certainly do this in Cartesian coordinates, but trust me, it's going to be a lot easier if you evaluate it changing to polar coordinates. Now, let's first just take a look at what this region looks like to give you a sense. Right, so the blue dome, we have our blue hemisphere there, right? That's z equals 1 minus x squared minus y squared, or the square root of 1 minus x squared minus y squared. So that's our hemisphere. And then we have y equals x squared plus y squared. That's the cylinder right here. And so what we're trying to do is we're looking at, for a volume that is below a surface and above the xy plane. So we can certainly use a double integral to evaluate this. And because if you look at the cross section here and you look at the shapes that we're dealing with boundaries delineated by circles, which is why you want to convert to polar coordinates. And just notice that this cylinder crosses through quadrant 1 and quadrant 4. Okay, so those are the quadrants of interest. So think about how you might convert that to polar coordinates. So give this a shot on your own, and then when you're ready to see the solution, so pause it, try it, and then resume to see the solution. Okay, so let's look at this, and I'm going to erase whatever just happened there. All right, so you're going to want to convert to polar coordinates. And remember, converting from Cartesian to polar coordinates, that r squared is equal to x squared plus y squared, x is equal to r cosine theta, and y is equal to r sine theta. So starting by looking at the graph of the circle right here. So x squared plus y squared, so converting that to polar is going to be r squared. And y becomes r sine theta. So it's going to be r squared minus r sine theta is equal to 0. So what we're trying to do is we're trying to set our bounds. And remember that we have to set bounds for theta and for r. So right now I'm trying to figure out what these bounds for r might be. And so for r, we're going to have to go through and we can set this to r sine theta is equal to r squared. And then dividing both sides by r tells us that r is equal to sine theta. So if we look back at our figure here, we can start to imagine that, okay, maybe, so we're set by the unit circle. So our max is going to be r is equal to sine theta, and our min then is going to be 0. And now let's think about this piece right here. We have z is equal to 1 minus x squared minus y squared. And so that's going to be our function that we are integrating. So let's set this up. So v is going to be equal to the double integral over our region, which we set by our limits on theta and r, times, so we're going to integrate our function, which is z is equal to the square root of 1 minus x squared minus y squared, times dA. And so now let's convert z to polar coordinates. So z, x squared minus y squared, well, we can say this is equal to 1 minus in parentheses, x squared plus y squared, which is r squared. So z is equal to the square root of 1 minus r squared. And we still have our dA. Okay. And so let's think about how to set these bounds. So be careful when you're setting your bounds for theta, because here we're only in quadrants 1 and 4. So you may be tempted to integrate from minus pi over 2 to pi over 2. However, sometimes you end up when you set your bounds like that, you end up canceling yourself out, and you end up getting a volume of 0, which you can see in this case, the region encapsulated by this cylinder and this hemisphere is not 0. So what we're going to do is we're going to call upon symmetry. We're going to notice that quadrant 1 and 4 are symmetric. So we're only going to integrate over one quadrant, but we're going to double our integral. So we're going to put 2 in front because of symmetry. So we're going to do 2. And we're going to go from 0 to pi over 2 for theta. And we're going to go from 0 to sine theta for our radius. And our function that we're integrating is going to be the square root of 1 minus r squared. And remember, dA, when you convert to polar coordinates, always becomes r dr d theta. Okay, so we're going to start integrating in terms of r, so our dr portion. And so we're going to start with a u substitution. And we're going to let u equal 1 minus r squared. So then du is going to be equal to minus 2r dr. And solving for dr, we get dr is equal to du over 2r. Minus du over 2r. Okay. So now what we're going to do is we're going to evaluate this. So using our u substitution, zooming in here, we have the integral of u to the 1/2 r times minus du over 2r. So you can see that our r's are going to cancel, and we end up with, once we integrate, well, let me just rewrite this. We end up with minus u to the 1/2 du. Okay, and so then when we integrate, we end up with u to the 3/2 times 2/3. So minus 2/3 u to the 3/2. Okay, and so then we plug back in 1 minus r squared for our u. And, oh, I'm sorry, I lost a half. Minus a half. There we go. Times our half. The 2's cancel. There we go. And we end up with minus 1/3 u to the 3/2. Okay, so I'm going to write that in. And remember, we still have a 2 out front. And so that becomes, we get 2, and we're going to integrate from 0 to pi over 2. And we have minus 1/3 times 1 minus r squared to the 3/2. And we're going to evaluate from 0 to sine theta d theta. Okay, so I'm going to start a fresh sheet for this, and we're going to sub in sine theta for r. Okay, so we have keep going on our warm-up. Sorry, I have a visitor who's digging into all the class notes. Okay, let's keep going. Okay. So now we're going to have, let's pull out our 1/3. So we're going to have 2/3 we're going to have 2/3, and let me just write where we left off up top just so it's a little easier for us to work with. So our last step we had 2, and we had 0, we went from 0 to pi over 2, and we had minus 1/3, and we had 1 minus r squared to the 3/2, and we're evaluating from 0 to sine theta d theta. Okay, so if we pulled out a positive 1/3 there, and we still have 0 to pi over 2, and we have our minus, and we have to plug in sine theta, so we have 1 minus sine squared theta, and that's going to be to the 3/2. And then we're going to subtract off 1 there's a double negative there, so we're going to add 1 minus 0 to the 3/2, which is just going to be 1 d theta. So this is going to be equal to 2/3, and then we're going to go from 0 to pi over 2. Let me just rearrange the order here. So we're going to have 1 minus 1 minus sine squared theta to the 3/2, and then d theta. Okay. Now, I'd like to try to simplify this as best we can before we even proceed to any integration. So, some things you might notice, thinking about some trig identities, is that, remember, 1 is equal to sine squared theta plus cosine squared theta. And so 1 minus sine squared theta is equal to cosine theta. So this whole piece can be rewritten as cosine theta. Cos squared theta. So let us simplify a bit. And so this is going to be 2/3. And we're going to go from 0 to pi over 2 of 1 minus cosine squared theta to the 3/2 d theta. Okay, And so we have cosine squared to the 3 halves. So for our power, it's going to be 2 times 3 divided by 2. And so this is going to be 1 minus cosine cubed. So we have 2/3. And then we're going to go from 0 to pi over 2 of 1 minus cosine cubed theta d theta. All right, now we're going to do something a little bit sneaky. And we are going to rewrite our 1 minus cosine cubed theta as, we're going to make this, we can rewrite cosine cubed theta as cosine squared theta times cosine theta, right? So this is the same thing as cosine squared theta cosine theta. Okay, and so we can rewrite cosine squared theta as 1 minus sine squared theta. And I know this is starting to feel very circular, but there's a reason we're doing this, because we're trying to set up the inside of our integral to be much nicer to work with for a u substitution. And you'll see what I mean momentarily. So this is going to be equal to 2/3 times the integral from 0 to pi over 2. And then we're going to have 1 minus sine squared theta times cosine theta d theta. Okay, now we're ready for our u substitution. And so what we're going to do is we are going to let u be equal to sine theta. Right, so then that way du is equal to cosine theta. Our end goal here, d theta, oh no. Our end goal here was to cancel out this cosine theta. And so d theta is going to be equal to du over cosine theta. Right, and so this can then be written as 1 minus u squared times, so let me rewrite this down here. We have the integral of 1 minus u squared, and then we have cosine theta du over cosine theta. So then all we're dealing with is 1 minus 1, which is 0. So then all we're dealing with is minus u squared du. Okay, so let's keep moving. I'm going to add one more page again. All right. So now our next piece is going to be, we had our u sub, and we had the integral of 1 minus u squared cosine theta du over cosine theta. Right, so this is going to be, all right, so let's break this up into pieces. All right, so this is going to be the integral. So this 1 we're going to pull out. We can split this into 2 different integrals is what we're going to do. So our integral before was going to be 2/3 times the integral from 0 to pi over 2 of d theta, so that's our 1, minus 2/3 times the integral from 0 to pi over 2 of, then we had our 1 minus sine squared cosine theta d theta. Okay, so with our u sub, right, this piece became the integral of 1 minus u squared du, which was just going to be equal to u minus u cubed over 3. And so for these u's, we had to plug back in sine theta. But then for this one right here, you have to be careful, is we're just integrating d theta and we're getting theta. So now it's going to be equal to 2/3. This one's going to be theta minus, this one is going to be u, which is sine theta, plus 1/3 sine cubed theta, and we're going to evaluate this from 0 to pi over 2, and this is going to be, it's going to come out to 1/3 pi minus 4/9 when all is said and done, which is approximately 0.60. Okay, so that was a hefty warm-up there. So now that you're good and warm, let's move on to converting triple integrals in Cartesian coordinates to first cylindrical coordinates. All right, so for cylindrical coordinates, here's how they're related to Cartesian. We have x is going to equal r cosine theta. So it's very, very similar to polar in a few ways. So x is going to be r cosine theta. Y is going to be r sine theta. So thinking about a cylinder, right? So the cross section of a cylinder is just a circle. So that's very similar to polar. But then we have this z component. And in cylindrical coordinates, z is just going to be equal to z. So then z is z. There's no conversion necessary there. So we could have evaluated our integral in the warm-up using cylindrical coordinates as well. And so let's define our region of integration as E, because this is a triple coordinate system. And so E is going to be our region, and it's going to be defined as equal to, and this is in E is in Cartesian coordinates, so it's going to be a function of, it's going to be in terms of x, y, and z, such that x and y are contained in D, which is just our two-space coordinate system. And we're going to have some term that we're going to call u sub 1, or some function, u sub 1, some lower bound function of x and y. It's going to be less than or equal to z. And our upper bound, so z is going to be less than or equal to our function in terms of x and y. So then if we were going to write this for cylindrical coordinates, let's say then D is equal to So it's going to be a function of r and theta, similar to polar coordinates, such that d is less than or equal to theta. This isn't a d, this is an alpha. I can read my handwriting super well. Okay, so this is an alpha, which makes a lot more sense. Alpha is less than or equal to theta is less than or equal to beta. Okay, so that's going to be our theta. And then relating to r, we're going to have some function of theta for our lower bound. It's less than or equal to r is less than or equal to some function of theta, h2 for our upper bound. And don't worry, we're going to go through an exercise looking at this where it'll be practicing with it will make it more concrete for you. It's pretty abstract still right now, I'll admit. Okay, so let's go through our formal definition now that we have our regions E and D set up and defined. So we're going to do a triple integral over our region E, defined up above, for a function in terms of x and y and z. dv can be converted to cylindrical coordinates as follows. So it's going to be equal to, so we're going to start with theta on the outside, and we're going to go from alpha to beta. Then r is going to be some function in terms of theta to the upper bound, also in terms of theta. And then finally, we have our z, which is going to be in terms of both x and y, but in this case, because we're going to be in cylindrical coordinates, it's going to be also in terms of theta and r. So it's going to be u2 r cosine theta r sine theta, so that's upper, and our lower bound, u sub 1, is going to be another function in terms of both r and theta once again. Okay, and now we have to convert our function to cylindrical coordinates. So x is going to be r cosine theta, y is going to be r sine theta, and z gets to be stay z. And then similar to spherical coordinates, we're going to have r times dz dr d theta this time. Okay, so we still have 3 length dimensions here to make a volume. Okay, so let us go through an exercise using cylindrical coordinates. Okay, so a solid E lies within the cylinder. X squared plus y squared equals 1. Below the plane, z equals 4. And above the paraboloid, z is equal to 1 minus x squared minus y squared. Okay, so you can see right here that this plane is our z equal to 4. So our z-axis is up here. Our x is coming out. Our y is going to the right. And we have our cylinder, which is purple, which is defined by this x squared plus y squared is equal to 1. We have our paraboloid down below, which is z is equal to 1 minus x squared minus y squared. And so we're looking within the cylinder, below the plane, so all this place below the plane, but above the paraboloid. So our base is going to be defined by the top of this paraboloid. So it's all this region in here that we are interested in. And so let's just start by looking at some coordinates. Let's pick out some coordinates here. So intersecting with the xy plane, if we look right here at this outer extent of our cylinder, it's going to be 1, 0, and 0. Okay, x is 1, y is 0, z is 0. And so the point on up here is z equals 4, and so that's going to be 0, 0, 4. Then I have one more point I want to show you, and that is the very top of this paraboloid. And that very top of the paraboloid is going to be the point 0, 0, z equal 1. And the gray is just the xy plane. That's all that gray is right there. And so one other thing to notice is that this we can write as z is equal to 1 minus r squared. Once again, x squared minus y squared is minus r squared. And let's see. And of course, x squared plus y squared is equal to r squared is equal to 1. And so let's start by thinking about our region. And we're going to call our region E. Right. So this is going to be, we're going to be using r, theta, and z, such that 0 is less than or equal to theta is less than or equal to 2 pi. Since we're going all the way around, so in terms of theta, we're going from 0 to 2 pi unit circle, or circle. We're going to go full 2 pi or 360 degrees. And for our radius, we know that r squared is equal to 1, so r is equal to 1. So we're going to go 0 is less than or equal to r is less than or equal to 1. And then finally, we can look at our limits for z. So we have z is equal to 1 minus r squared. It's going to be our lower limit, which is going to be less than or equal to z, which is going to be less than or equal to our upper bound for z, which is z equal to 4, that flat plane. Okay, so now we have set up our extents. And what we're going to do is, let's say that for this problem, let us try to find mass. We're going to find the mass. So remember, we know that triple integrals can get us a volume within defined boundaries in 3 space. But if we know density, we can take density and multiply by dV and integrate over that and get mass. So we want to find, let me just zoom back in, I don't know what happened. There we go. So we want to find the total mass if density, so this row is density, and I'll just write that up above to be clear. So if density is proportional, so this alpha is the proportionality symbol. So you could just multiply distance by a constant or divide by a constant. It's proportional to distance from the axis of the cylinder so we're going to find the mass over our region for mass of E. Okay, so we need to set up a function describing this relationship. So let's set this up. We can say that f of x, y, and z, and we're going to give a constant of proportionality. It's going to be equal to k times the distance from the axis of the cylinder. So k times x squared, the square root of x squared plus y squared. It's our cylinder. And another way we can write this is k times the square root of r squared, since we're dealing with cylindrical coordinates. So it's going to simply equal kr, which might make more sense to you, k times the radius, which is the distance from the axis of the cylinder. So mass will be able to be found if we took the triple integral over our region times kr, which is our function, and we're going to do, it would be our function dv, but because we're in cylindrical coordinates, dv is going to become r dz dr d theta. Okay, and so now let's write this out with our limits. So we're going to go from 0 to 2 pi. For theta, we're going to go from 0 to 1 for r. We're going to go from 1 minus r squared to 4 for z. And then we have kr squared dz dr d theta. Okay, and so starting on the inside, we're going to go from 0 to 2 pi, 0 to 1. Then kr squared dz, dz just becomes k r squared, z evaluated from 1 minus r squared to 4, and we still have dr d theta. K is a constant, we can pull that to the outside. And so let's add a new page and keep going. So this is going to be 27.1. Okay, and so let's pull k to the outside. So it's going to equal k. And then we're going to go from 0 to 2 pi still. And then we have our 0 to 1. And then we have r squared times z, and we need to plug in 4 for z and 1 minus r squared for z. And so we end up with 4 r squared minus 1 minus r squared. Minus r squared times 1 minus r squared. There we go. And that's going to be times dr d theta. And we can simplify this a slight amount. And so this is going to be equal to k times the integral from 0 to 2 pi times the integral from 0 to 1 of 4r squared minus r squared plus r to the 4th. The minus r squared times minus r squared is r to the 4th, dr d theta. Now we have to integrate this in terms of r, and so it's going to be k times the integral from 0 to 2 pi times 4 r cubed over 3 minus, I just realized how silly I was with the way I wrote this out, but we'll get over it, right? 4r squared minus r squared is 3r squared. So let's just integrate that 3r squared piece, which is much nicer. So we're going to have 3r cubed over 3, which is just r cubed, plus r to the 5th over 5. We're going to go from 0 to 1. d theta. And so this is going to give us k times the integral from 0 to 2 pi of 1 plus 1 minus 0, 1 plus 1/5 minus 0, d theta. And so 1 plus 1/5 is just 6/5. 6/5 d theta, which is just going to, when you integrate that, it's just going to be 6 theta over 5 times k. So this is going to be equal to k times 6 theta over 5, evaluated from 0 to 2 pi. And so it's just going to become k times 12 pi over 5. And that's going to give us 12 pi k over 5 is the mass. Okay, so that was our example with cylindrical coordinates, and you'll be practicing this more when you go through the assigned homework problems. In the meantime, let's learn a little bit about real spherical coordinates. So with spherical coordinates, we can still convert from Cartesian to spherical coordinates. And so this is a little bit different. So instead of r squared is equal to x squared plus y squared, we are going to now define the radius of a sphere as rho. So the Greek symbol rho. And this does make me a little nuts because in physics, we still use r in the definition of spherical coordinates, but I'm going to stay consistent with your book and use use rho, but just know that rho is very similar to radius. So we have rho squared is equal to x squared plus y squared plus z squared. And x is going to be rho sine phi cosine theta, and y is going to be rho sine phi sine theta, and z is going to be rho cosine phi. Okay, so here's the thing. So what we're now doing is we're thinking about a sphere, and in spherical coordinates, we look at the spherical wedge. And so some things I want you to notice. So theta is still just how you would imagine theta. So down here, we have the XY plane. So you're looking down at the XY plane. So theta still acts as theta would normally act. Theta is measuring the angle from the x-axis, right? So when you're dealing with spherical coordinates, you're still taking, to get x, you're still taking cosine theta. To get y, you're still taking sine theta. And in spherical coordinates, you don't, when you're in the xy plane, that's when z is 0. So now we are introducing another angular measurement, and that is called phi. And the angle phi is measured from the positive z-axis. So phi is measured from z. So the radius, rho, is going to be, it's going to be rho times cosine phi, because the reference for phi is the z-axis. So whatever your axis you're referencing, you take the cosine. So for z, it's rho cosine phi. For x now, you could sweep out from the x, but then you can also be elevated in 3 space, and you could be referencing the z-axis. So for x, it's going to be sine rho times sine phi times cosine theta, because your reference for phi is referencing, once again, the z. So you take the sine of phi and then the cosine of theta, because theta references x. So for y, you're doing rho times sine phi sine theta, because you're not directly referencing the y-axis in either of these cases. And so for the spherical wedge, our bounds, our region, is going to be defined as E is equal to, and it's going to be a function of now rho, theta, and phi, such that A is less than or equal to rho is less than or equal to B. Okay, so we're going to have some lower limit. So this would be A right here, for example, and some upper radius limit. So this would be B, so going out toward B. And then alpha is going to be less than or equal to theta is less than or equal to beta. Okay, so that is still sweeping out by theta, right? And so theta here, this lower, whatever the lower limit on theta is going to be alpha, and then going out to here is going to be beta. So this would be alpha, beta. Okay, so that's just, we're just projecting onto the xy plane, so it's a little easier to see. And then we're going to also have our phi, and phi, we're going to have C is less than or equal to phi is less than or equal to D. Okay. And so with phi, what we're doing is we're going, this would be, this angle right here would, for example, be C, and down to here would be D. Okay, so we're in 3 space. And now what I would like to do is to just keep in mind that for a couple more things. So A is going to be greater than or equal to 0, right? We're going to have some radius. Beta minus alpha has to be less than or equal to 2 pi. And D minus C has to be less than or equal to pi. Okay, because still in the xy plane, we're still sweeping out an entire 2 pi circle. With reference to Z, we're just sweeping out a quarter circle. So it's just going to be, or a half circle. So it's just going to be pi, right? So it's going, we're just looking at sweeping reference to the Z. So referencing the Z, you can go pi over 2, and then if you keep going and I break my arm, right, downward, pi. Okay, so that's it. You can only go pi. We don't go all the way around there. So we just have a positive and minus Z. All right, let's do one example here, and bear with me. Actually, oh, sorry, one more thing, of course. Let's just talk about our conversion. So our conversion is going to be from Cartesian to polar coordinates. We're going to do the triple integral over E for our function of x, y, and z dv. It's going to be equal to, all right, so for our d phi, let's start there. We're going from C to D for phi. And for theta, we're going from alpha to beta. For rho, we're going from A to B. Then our function, I know this, So it seems really cumbersome and really complicated right now, but trust me, when you're trying to evaluate the volume of something spherical and you have to convert it to Cartesian coordinates, that's when it's messy. It's when you're putting it directly in to spherical coordinates, it actually works out much nicer, much more simply. So now x is, of course, rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. Okay, now get this. Now dv in spherical coordinates becomes rho squared sine phi d rho d theta d phi. So here's the thing. Once again, like I said, dealing with cylindrical coordinates, dealing with polar coordinates, our units have to work out. So the units attached to rho are length squared. Okay, that gets you to area. D rho, that's also length. So that gets you to cube. So here's the thing though, we want to, so now then we have to have our sine phi in there too, because that's an adjustment from referencing the z plane. So we're converting back. And then we have d rho, d theta, d phi, which are d theta, d phi are just angles, so there's no unit on those. So the units work out. And we're not going to go through the derivation of this, but just know this is how you convert between the different coordinate systems. So we're going to do one final example today. And so you've been really good and really patient, even though there's no one here live and it's just me and you saw the crazy cats in the background. All right, so our last exercise, we're going to be looking at ice cream. Yay! So we're going to use spherical coordinates to find the volume of the solid that lies above the cone. Z is equal to the square root of x squared plus y squared, and below the sphere, z is equal to x squared plus y squared plus z squared. And so it's a little tricky to see, so I am going to try to outline this the best I can, maybe with red. Okay. So here is our lower extent of our cone. So there's the lower extent of our cone. And then we have this kind of hemisphere of ice cream in there. I tried to make the ice cream green for pistachio, and I tried to make the cone orange, but it's a little difficult to see. Didn't come out super well. But this is what we're integrating to get the volume of this object right here, this ice cream cone. And so then if we were to look, maybe I'll do it like right here, this coordinate would be 0, 0, 1. And so for a cone in spherical coordinates, what this is actually, it's just theta is phi over 4 is what we're looking at there. Okay, so we're just going from z to pi over 4 because going all the way to the xy plane would be pi over 2. And then we also have this cone, z equals the square root of x squared plus y squared. Okay, so we have our upper bound by the sphere, this lower bound, outer bound down here by the cone. And so notice that the sphere passes through the origin, and its center then is going to be 0, 0, 1 half, which we can see right here. That's the center, 0, 0, 1 half. So now let's start doing some conversions for our coordinate system. So things we notice, z equals x squared plus y squared plus z squared. And x squared plus y squared plus z squared is our definition of rho squared, which is z. And another thing we know is that z is equal to rho cosine phi. So we can rewrite the equation of a cone as follows. So we have z is equal to the square root of x squared plus y squared. So let's rewrite z as rho cosine phi. And that is going to be equal to, now r is meaningless to us in spherical coordinates. So x squared plus y squared equals r is not going to help us. So what we need to do is we need to plug in x is equal to rho sine phi cosine theta and so on. So we have x squared is going to be rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Now, get really excited for some magic, some trig magic. Okay, so let's try to simplify this a little bit. So what we have is, you notice we can pull out a rho squared. So we have rho squared. What else can we pull out? Well, we can pull out sine phi squared. And then we're left with cosine squared theta plus sine squared theta. Ooh. Which is, I wish you guys could shout out with me, 1. And so we end up with the square root of rho squared sine squared theta. So if we take the square root of rho squared sine squared theta, we end up with rho sine theta. Sorry, I keep saying theta. This is phi. Rho sine phi. So we get rho cosine phi is equal to rho sine phi. And so we end up with cosine phi is equal to sine phi. And when is the only time cosine phi can equal to sine phi? Well, that is when phi is pi over 4. Okay. So, knowing this, let's start to set our bounds. So E, or region, with respect to with respect to rho, theta, and phi, we're going to have 0 is less than or equal to theta is less than or equal to 2 pi. Which hopefully makes sense, because if you look down at our ice cream cone, bird's eye view, looking down at the XY plane, it's going to look like a circle. We're going from 0 to 2 pi. So then we figured out our extents for phi, which we could have just done by looking at this cone here, if you know that it goes from 0 to pi over 4 for phi for a cone. But we verified that, so we checked it twice. And so we're going to go from 0 is less than or equal to phi is less than or equal to pi over 4. And then lastly, let's look at our rho. And rho is going to go, well, the lower extent for rho is going to be 0. And the upper extent is going to be z is equal to cosine theta. Okay. So, hold on one sec. Let me just adjust this. That's supposed to be phi. Because if you look back up here, we have our z, we have z is equal, we know z is equal to phi cosine theta, and then also z is equal to phi squared. So rho squared. So rho cosine phi is equal to rho squared, or it just tells us rho is equal to cosine phi. So that's where we get our outer extent for rho. Okay, now we're all set up, and now we can go through and finally do our spherical integral. And this will be the last thing we do in this lecture. It'll take a little bit, but hang in there. So this is 27.2. Okay, so let's set up our integral. So V is going to be the triple integral over E dV, which is going to be, we're going to go from 0 to 2 pi. For theta, we're going to go from 0 to pi over 4. For phi, we're going to go from 0 to cosine phi for rho. And remember, dV in spherical coordinates becomes rho squared sine phi d rho d phi d theta. So this is going to be equal to the integral from 0 to 2 pi times the integral from 0 to pi over 4. And so now we have rho squared sine phi d rho is the piece that we're looking at. And so rho squared d rho becomes rho cubed over 3. And we still have our sine phi. We're going to evaluate from 0 to cosine phi. And we still have our d phi d theta. All right. And so now we're going to have, we go from 0 to 2 pi. We're going to go from 0 to pi over 4. And we have cosine cubed over 3 phi sine phi d phi d theta. So then what we're going to do is we can actually, we don't need to even completely go in this order here, because you can see that cosine cubed phi, sine phi have nothing to do with theta. This 0 to pi over 4, this our extents for phi don't have anything to do with theta either. And so what we can do is we can separate this out if we wanted to, and we can do it separately, and we can go from 0 to 2 pi d theta plus 0 to pi over 4 cosine, not plus, times times 0 to pi over 4 cosine cubed phi over 3 sine phi d phi. So just integrating d theta gives you theta. Going from 0 to 2 pi just gives you 2 pi. So we end up with 2 pi. And then we could also pull out that 1/3. We end up with 2 pi over 3 times the integral from 0 to pi over 4 times sine phi cosine cubed phi d phi. All right, so I put off the u substitution long enough. I'm going to just put it up here since there's some room up here. We're going to let u equal cosine phi. So then du, of course, becomes minus sine phi d phi. So d phi is going to equal minus du over sine phi. So then we can get rid of the sine phi. So we have the integral of sine phi u cubed minus du over sine phi. So we have minus u cubed du, right? Which is going to be minus u to the 4th over 4. Okay. And so that is going to give us 2 pi over 3. U is cosine phi, so it's going to be minus cosine to the 4th phi over 4. And we're going to evaluate from 0 to pi over 4, which gives us pi over 8. All right, that is all for this week. And so tune in next time. And, well, if you're finishing at the end of the week, have a great weekend. But otherwise, take care, be well.